Hello, welcome to Lab 4. The purpose of this lab is to model a spring mass system. In order to do this, we will analyze a spring mass system using Tracker, construct a computer model based on physics, compare this model to our observation, explain why this model is a good approximation of our observed system, and answer the what if and what does it mean questions. For our observation, we will be using the same system as in Lecture 1 of Week 9. The calibration and orientation of our coordinate system are exactly the same as in that lecture. The only difference is the weight is being released from a different position. Here are the graphs of the x and y position of the weight as a function of time. The system we observed consisted of the weight, earth, and spring. This is the weight's mass, and here is its initial position. We will assume that the acceleration due to gravity is 9.8 meters per second squared, and that our spring has negligible mass. In the analysis in Lecture 1 of Week 9, we calculated the spring's stretch constant and its relaxed length, which we will use in our model. We will be modeling our system under the assumption that our spring is ideal, and the only forces acting on the weight are the gravitational and spring forces. I will now cover the physics applied in my model. First, to calculate the spring force, I used Hooke's law with the value shown in the previous slide. I used Newton's second law to calculate the gravitational force and to update the weight's velocity over time. To track its position, I used the position update formula. To calculate our system's change in total energy, I used the energy principle, assuming that the total thermal energy change of our system is equal to 0. As you can see, the total change of our system's energy is equal to the change in kinetic energy plus the change in gravitational and spring potential energies. I used the following formulas to calculate the change in kinetic energy, the change in gravitational potential energy, and the change in spring potential energy. I will now discuss my computer model. As you can see, I have set the weight's mass to that of the observation. The initial position has been set appropriately, and since the weight was dropped from rest, its initial velocity was 0. These lines extract the position data from our observation in Tracker. Here you can see j hat is set to point in the positive y direction, and g, k sub s, and l naught have been set to the values shown earlier. These three lines are used to calculate the stretch of our spring. Here you can see the formulas for calculating the kinetic energy, gravitational potential energy, and spring potential energy. We will use these as the initial energies of our system. Here, we calculate the gravitational force and the spring force, and set the net force equal to their sum. Once again, we calculate the spring stretch. Here, we calculate the final kinetic and potential energies of our system, and subtract the initial from them to find the energy change for each time step. These lines take the data we extracted from the observation to compare the position of the model to the position of the observation. Here you can see the position of the model, the blue ball, and the observation, the red ball, over time, with the blue and black arrows representing the spring force and the weight force respectively. Here you can see a graph of the energy of our model, with the blue line being the change in kinetic energy, the red, the change in gravitational potential energy, the green, the change in spring potential energy, and the yellow being the total energy change of our system, which our model calculated to be approximately 0. As you can see, our model did a fairly good job of modeling the observation. My explanation for the differences between the two is experimental error and the fact that the spring in our observation is not really an ideal spring. Now, we will answer the two questions. First, what does it mean? Does our model satisfy the energy principle? We assume that there was no transfer of thermal energy, so the total change in energy of our system is equal to the work done by the surroundings. Since our system consisted of the weight, earth, and spring, there was no work done on our system by the surroundings, so the change in total energy should be equal to 0, which is what our model calculated. Next, what if? Estimate the x and y oscillation periods. To do this, I took the time period for 4 oscillations in the x direction, and then for 4 oscillations in the y direction. I then divided each by 4, which gave me a result of 1.638 seconds for the x period and 1.520 seconds for the y period. This concludes Lab 4.